So hello everyone, welcome to today's Games, Decisions and Network seminar. Thank you all for joining us today. It is my pleasure to introduce our distinguished speaker today, Professor Michael Jordan from UC Berkeley. I guess we may not need too much introduction, but let me just quickly go through the process. Professor Jordan is the Pei-Hong Chen Distinguished Professor in the Department of EECS and Department of Statistics at UC Berkeley. His research interests bridge the computational, statistical, cognitive, and biological sciences. He has made countless significant contributions and laid foundations for many of the topics we have seen today in machine learning. Professor Jordan has won numerous titles and honors that one can think of in computer science, applied mathematics, statistics, and engineering. He is a member of the National Academy of Science, a member of the National Academy of Engineering, as well as a member of the American Academy of Art and Sciences. He's a fellow of the American Association for Advanced of Science. He has also been named a Neyman Lecturer and Medallion Lecturer by the Institute of Mathematical Statistics. He received the Alf Grenander Prize from the American Mathematics Society in 2021, the IEEE John von Neumann Medal in 2020, the IJICA Research Excellence Reward in 2016. He is also the fellow of AAAI, ACM, ASA, CSS, IEEE, IMS, and SIAM. In 2016, he was named the most influential computer science worldwide in an article published in Science. Today, we are very honored to have Professor Jordan in the series, talking about his recent interesting works on decision-making in machine learning and game theory. As the title suggests, this will be quite relevant to the theme of our seminar series, which is on the foundations and applications of game theory, decision theory, and network theory, with speakers and audience from the intersection of economics, operations research, control, and game theory. Before starting, let me make a very brief announcement for the audience, so please remain muted during the talk. If you have any questions during the talk, please type them down in the chat box, and we will relay them to Professor Jordan. We will also have time for Q&A in the end of the talk, and feel free to just raise your hand and we will let you unmute yourself and ask questions. So without further ado, please join me in welcoming Professor Jordan, and thank you very much for joining us today, Professor.
All right, well, thank you, very nice introduction, Kai-Shing, and thanks for including me in your series. And so good morning or good evening or good night, wherever you are in the world. So I do have something to say about games and decisions, and maybe a little bit about networks in any case. And as you can see in my title, it's kind of an ambitious title. I do want to say a little bit about machine learning and kind of why I'm interested in games and decisions these days. So it's helpful to think of statistical machine learning as not really a new field, but sort of an engineering discipline that's emerged out of computer science and statistics. A large amount of the work that's been done in the last several years is focused on pattern recognition. That's a terminology that comes out of the 1960s, signal processing and statistical literature kind of collaborating. And it builds on older traditions, however, that incorporated decision-making as well as pattern recognition. So the decision and inferential themes going back into the 1930s and 40s had patterns and decisions together. We've sort of lost decisions a little bit along the way. Pattern recognition and neural nets and so on have become the highlight of the era. But I'm going to argue very strenuously that that's a mistake to not also focus equally on decision-making. So we're going to be interested not just in simple decisions that are thresholding of some kind of a pattern recognition system, but really high stakes decisions and sequences and multiple decisions and so on and so forth. So I like to also not just think like an academic. I like to put on a hat of someone who spends time in industry and looks for the themes around us. So this is my little short history of machine learning, which I do think is best thought of as a new engineering field. It is in industry, 30 years old or more. Already in the 1990s, you had companies like Amazon building fraud detection systems that allowed them to do e-commerce by analyzing data at very large scale and very adaptively. Even more importantly, modeling supply chains at scale. Now we're up sort of 1 billion products by hundreds of millions of people. And that was done with actually random forests and large numbers of computers, kind of the glimmer of what became the cloud, and massive data sets and so on. So in some sense, that kind of pattern recognition side hasn't really changed that much. It got larger. I think the second generation became when people realized a lot of the data was about humans. It was their transactions, their preferences, and so on, not just about supply chains. And so recommendation systems emerged. Again, the underlying machinery was very much the same: large data sets, matrices, and gradient descent kind of methods, and so on, random forest as well. Let's identify the third generation now as the maybe the era we're currently in, involving neural nets and so on. Again, large amounts of compute, gradient-based algorithms, and really just kind of the data changed a bit. So instead of just being about transactional things and what humans do, it's about things like speech and vision and translation. So when the computer learns from that kind of data and imitates that kind of data, it looks like the computer is intelligent. And I think that the AI buzzword has gotten affixed to this activity now, sort of unfortunately, in my view, because it's not really deeply intelligent. It's just simply taking human data and fitting regression models to that data. Nonetheless, I think in the meantime, there's something even more important emerging. It's been emerging for quite some time. And it's really best thought of as not a single agent learning in a world and replacing a human or imitating human intelligence. It's really the emergence of markets at planetary scale, which involve data analysis and involve all kinds of asynchronous decisions at all kinds of levels by all kinds of actors, partly human, partly non-human. And this, to me, is the emergence of this new field of engineering. So it definitely involves decision-making as well as pattern recognition, and all of the machine learning technology we've been seeing augmented suitably to reflect this much, much larger scope. And as an academic now returning to that, this is exciting to me because these are going to be brand new problems that aren't just simply how to make gradient descent work better. So let me say just a little bit more about decisions. And I like to think about the example of, say, you go in to see a doctor, and in a couple of years, the doctor will measure your genome, measure all kinds of things about your body, all kinds of new sensors will be used. So maybe there's 100,000 dimensional feature vector that comes out of your, that's measured for you in that moment. And let's imagine that's been put into the world's largest neural net that takes all of the world's medical knowledge and has been trained on that. So you might think that's going to be a really, really good doctor. So imagine that one of the outputs of the network is a prediction about whether you're going to have a heart attack or not. And suppose that based on the historical data, a number over 0.7 suggests that you're about ready to have a heart attack. And suppose that your number is 0.701. All right, so you're over a threshold. Should you take that as a decision and think about all the consequences? And I argue, no. The first thing you're going to do with a real doctor is you're not going to simply accept that. You're going to ask sort of whys and wherefore questions. First of all, you're going to ask, what are the error bars around that? We don't have really good error bars in the modern pattern recognition era. But you're going to ask for error bars, and error bars aren't just like little Gaussian noise or something. It's going to be having to do with the uncertainty of how that decision arose or that thresholding arose. What data was used? Is the data recent? Is it stale? Is it from a different machine, or is it from the same machine? Is it from a different population, or is it from a population that's relevant to me? And so on and so forth. Then you're going to also ask other questions that have a counterfactual flavor. What if I were going to exercise differently? Or what if I were going to change my diet? And I'm going to also think about things about my past, maybe that I had some childhood disease or something that I hadn't thought about before. And you realize that all that so-called knowledge that went into building that neural net, actually, you didn't use all the world's medical data, because data that's relevant for my current decision will come out in that moment as I start to think about it, and as we start to do counterfactuals of thinking about other things that could have happened that didn't actually happen. And that's what reasoning around a decision involves. All right, so I hope you get a flavor that decision-making is far from just taking a threshold of a statistical system. It's all kind of a dialogue, really, about decision-making. And this feels to me more like a market. It feels like you go into a situation and you think about the situation, you think about the context and what else is happening, and then you think about things that are relevant in that moment. Now, it's never just one decision. So there's going to be several decisions that I make today, and some of them are on fast time scales, some of them are on slow time scales. It'll be decisions across a network because I'm linked to other people and their decisions affect mine and their data affect me and so on. It'll be over time, and I don't mean just over a small amount of time. I mean over years, like real world decision making. And then critically, it's going to start to involve scarcity and competition. I'm going to interact with others who want some of the same things I want, and maybe not all of us going to have it because there's limited amounts of it, including, for example, capacity constraints on highways or capacity constraints on restaurants. All right, so now let's try to bring in the pattern recognition thing and sort of see how to think about sort of gluing these together and the problems that arise. So a recommendation system, you all know what it is. Classical pattern recognition system looks at patterns from past purchases and does some clustering. It matches people up and makes new recommendations. Again, that's often thought of as a decision-making system. It's giving at least recommendations for decisions, but that's really not a very good way to think about it, because in the real world, if you start making recommendations, you will create congestion. So if you recommend the same movie to everyone, I mean, maybe, a million people are using your app and it starts to make recommendations. Could be that you recommend the same movie to 500,000 people. And that's no problem because there's no scarcity in the virtual world. You can copy the bits as many times as you want. But in the real world, there's scarcity. If you recommend the same restaurant to everyone, so everyone in Beijing is using your app and you start to make recommendations to people, you could recommend 10,000 people to go to the same restaurant, right? And now you've created congestion, and you can't just fix that by sort of load balancing in a naive way, deciding that some people get to go and others not, or tossing a coin. You're really leaving human value on the table here. You're not thinking enough about who really wants it, and you're not understanding the utility of the people involved. Right. And so that's really, I think, the mistake that a lot of the IT companies make. They think they know your browsing history, and so they know a lot about you. They can predict what you really want, and they'll give you what they think you really want. And I hope you agree that that's kind of just farcical. They're not going to know what you really want. You don't even know what you really want. Things are contextual. In the moment, you're going to think about which restaurant you might want to go for reasons you never thought of before. So that, again, feels like more like a market. Recommending streets to drivers. Similarly, there should be some kind of a notion of a market. Who cares to get there fastest in that moment for what reasons? All right. So the alternative, instead of creating a recommendation system, a pattern recognition system, is to actually create a market. You're going to link producers and consumers, two-way market. You'll have maybe diners on one side, restaurants on the other. They'll make bids to each other. They will set prices, perhaps. And this isn't just arguing that let's replace machine learning with microeconomics and game theory. It's really an augmentation, because we don't perhaps know the preferences a priori. When I go to a restaurant in Beijing, I don't know which restaurant I like a priori. I haven't experienced them. Can't write down a list of all my preferences. And similarly, the restaurants can't say who they prefer. It's a very learning-oriented, adaptive market where all the preferences are being learned simultaneously with actually doing the matching or creating the prices and so on and so forth. So statistics came together with economics over the years, but really more just to measure things like time series. That's econometrics. This kind of statistics meets a full-fledged way game theory mechanism design. It's not entirely new by any means, but it's certainly not been a focus of most people doing research. I do want to note one person who definitely was focusing on this. That was David Blackwell. His work was definitely decision focused. He was a probabilist statistician, but he also was an economist and worked on algorithms, control theory, and so on. I luckily got to know David Blackwell when I first came to Berkeley, and definitely appreciated his perspective on all of this. Unfortunately, he was rare, and statistics, microeconomics links are not that strong. Statistics, computer science links are sort of stronger. That's machine learning. And then microeconomics and computer science, that's kind of algorithmic game theory. But this triad of coming together, David's kind of style is not as prominent as I think it critically needs to be. The other point is more like this algorithmic game theory argument, which is that markets act like algorithms. They act like intelligent systems. They're decentralized. They accomplish complex tasks. They do it over many years. They're adaptive, robust, and so on. So they look like AI, if you want to use that language, but they're not really thought of as part of AI. AI is about thinking and data analysis and so on and so forth. So again, I think that's a mistake, that we need to expand our horizons to have large-scale markets be the object of study. Here's just some things that I just kind of wrote down on one slide, some problems with the interface of ML and econ agents where you have to learn, you have to explore to learn your preferences, not just you're learning your preferences, you have to actively explore. As we'll talk about examples of that. Recommendation systems blended with markets. Again, if I have hundreds of thousands or millions of options, like the books I could buy or the restaurants I could go to, I'm not going to be able to have a preference on all of them. I can't even write it down. I can't even think about it. So I need to blend in a little bit of learning from other agents, like a recommendation system that helps me shape my preferences in a matching market, and then many other such problems. All right, so we want to discover healthy learning-based markets that are stabilized over long stretches of time. Again, definitely people have worked on aspects of this. I'm not definitely new to this, but it is not a common perspective in most of the subfields that are interested in these things, either control or economics or machine learning. Look at parts of this, but I really think we, because our systems are being really used in the real world, think the COVID outbreak or think transportation or commerce, they are machine learning systems, they are flowing, data is flowing around. We start to need to think at this level. All right, so now let me go down to a lower level. Let's start to do real research. Here's a little project I want to just use to exemplify what I've been talking about here. This brings together a very core problem in machine learning or statistics, which is the multi-arm bandit. So we have a bit of exploration and exploitation, and it brings that together with a core problem in microeconomics, which is the matching market. So Lydia Liu and Hori Yamani have been students with me at Berkeley working on this. So you all know what a multi-arm bandit is. I'm an agent and I have several options of actions. Each one of them has a reward distribution associated with it. I don't know the distribution a priori. So I try out my options and I get rewards back. And then I make a model of not the full distribution typically, but some aspect of the distribution. For example, a confidence bound on the mean reward might be something I would do. And then this algorithm, very famous upper confidence bound algorithm, says I'm going to pick the action that has got the largest value of the upper end of the confidence interval. All right, so that's a smart thing to do for a couple of reasons. One, if the overall distribution is shifted up to the right, I'm going to get good rewards from the distribution. I should pick that arm. But two, if the upper confidence bound is high because I have a lot of uncertainty, I should pick that arm because I should reduce my uncertainty and figure out if it's really a good arm or not. So those two ideas come together in one algorithm, and you could prove that the regret you have for this algorithm is logarithmic in the number of trials. That means the reward I get relative to an oracle that knew a priori which was the best arm to pick. All right, so hopefully many of you know this algorithm. Again, the core, this is a learning problem. It's not just kind of a regression problem where you're told a supervised label. This is a real learning problem. You don't know what the right action is a priori, and you figure it out over time, and you try to exploit. You try to perform that good action as you learn it. Okay, so that's on the statistics side. What about the game theory or microeconomics side? Well, here's a matching market. Buyers on one side, sellers on the other. Each of them are assumed to have preferences for the other side of the market, and they know the preferences a priori. You even consider maybe a centralized site which knows the preferences. And so here buyer number one prefers seller number 1 to 3 and then 3 to 2. Having written all those down, you can develop algorithms like the famous Gale-Shapley algorithm, which iteratively forms a matching between the two sides of the market so that there's a certain stability criterion which is met. Okay, so I think you can see where I'm going. We want to put these two ideas together. What if the participants in the matching market don't know their preferences, but they try out options on the other side of the market and get a reward, and then they adjust their preferences, and so you're both learning the preferences and you're doing a matching simultaneously. All right, so what happens there? Well, here's a little picture. Got two agents, the bear and the human, and they're picking these options. All right, now, so the question is, as a matter of modeling, what are you going to do when two agents pick the same arm? All right, so in our model, we treat this as a competition. We're thinking about congestion, and so if both of them pick the same arm, what we're going to do is that one of them gets the reward, the other gets no reward. So it really should be no reward, not 0 there. Which one of them gets the reward? Well, the arm, in this case, arm 2, has a preference back on the agents on the left side of the market. And those preferences are also unknown and perhaps stochastic and so on. So this is different from some, there is work on congestion markets in networking, where if two people pick the same arm, two agents pick the same arm, then neither of them get the reward. Okay, so you both sent packets down a channel, nobody gets through because there's congestion. And this is different here. We're assuming that one of them actually gets it, so it's more like a matching. All right, so we have a bandit market. You get noisy rewards, and there's some matching going on as part of the overall algorithm. We need to do some mathematics. We have to define a notion of regret here. Our regrets, I don't want to get into details here, but it's really straightforward. Assume you knew the preferences a priori. Assume you ran Gale-Shapley on those preferences. That would give you a certain matching. How well do you perform relative to that? All right. And here's an algorithm we've analyzed. We've analyzed some other algorithms, but this is one particular algorithm to get an upper bound. So you run the upper confidence bound algorithm for each agent for every arm. And then instead of using the means or known preferences for Gale-Shapley, use the upper confidence bound of values in the Gale-Shapley algorithm. So let's call that the GSUCB algorithm. All right. And can you prove anything about that? And the answer is yes. So you turned out that you get a logarithmic regret still for this. And that's a little bit surprising, because if I pick an arm and the bear also picks the arm and the bear wins, I realize that even though I like that arm, I may not be getting it in the future. So I better explore the other arms more than I otherwise would. So the bear causes me to explore more. And you might think that extra exploration, which is going to lead to more regret, could lead to a worse than a logarithmic bound, but it turns out it doesn't. However, there is a denominator term there, delta squared, which measures a reward gap, not between your own rewards for the different arms, but rather, that plus the gaps between you and the other agent. So if I don't overlap at all with the bear, that's going to be fine. We're going to be kind of operating in parallel. But if I have overlapping rewards with the bear, then those gaps will be small, and I'll get a larger constant in the regret. Okay, let me just mention some further applications of UCB in decision-making problems. Surprisingly, it hasn't been used that much in many of the classical machine learning decision-making problems, like reinforcement learning. Surprising, because it kind of reinforcement learning sort of somehow emerged from Bandits. But it's pretty typical of machine learning, again, to criticize a little bit, that people don't think about uncertainty very much. They don't think about confidence intervals very much, and so on. So you've seen that in reinforcement learning. It just becomes maximized reward, just kind of an optimal control problem. There's no exploration kind of built into the reinforcement learning algorithms. Okay, so with Qijin, Zheyan Anju, and Sebastian Bubeck, we decided, based on this previous work, to look at what happens when you add UCB to reinforcement learning. So again, I don't want to spend time on details. Here's your kind of standard Markov decision problem. As you probably know, there's a debate between model-based paradigm and model-free. Model-based means you form a transition model based on data, and then you plug that into a dynamic programming algorithm of some kind, or classical RL algorithm. The model-free paradigm is more like the Bandit situation. I simply try out actions, and I go uphill in some sense in average reward. Which of these is the better approach? All right, well, you can argue on various bases. Let's try to be theoreticians about it. Okay, so we'd like to analyze the regret on these two paradigms, not just the average reward accumulation, but the actual regret. All right, so to do that, we need an algorithm that has some kind of a notion of exploration. So here we've just taken QLearning. Again, I don't want to spend time on details. Hopefully you have seen this. There's QLearning in blue there, just kind of a Bellman style update. And then BT in red is a upper confidence bound. So we're adding a upper bound on our Q values, right? And the upper bound, as you see down at the bottom, scales in a particular way. And now we can do some theory on this. And I'm going to, on one slide, show you the state of the theory, not for just our work, but for existing papers and literature. At the top, you see model-based paradigm. So a number of authors have analyzed various model-based paradigms. And the upshot of that is that you can achieve square root of T regret. Okay, T is the number of time steps in the reinforcement learning trials. So square root of T is not log T. It's not quite as good, but it's pretty good. And by comparison, if you go down to the bottom part of the table, the top two entries there, QLearning with epsilon greedy and delayed QLearning, These are algorithms which are doing a little bit of kind of ad hoc exploration, like epsilon greedy is an ad hoc exploration technique. And there you can see that the regret is not square root of t. It's t or t to the 4/5, so not good. Right, but this new, or not new, just very simple add UCB to QLearning algorithm, we were able to analyze it, and it turns out it has square root of t regret as well. So in that sense, model-free and model-based paradigms are equivalent. They're comparable at least, and you can prefer one or the other based on other reasons, but just in terms of the raw regret, in terms of t, they're comparable. Okay, so I'm going to stop on that little thread there, but just to say that we're working on lots of other kind of confidence intervals means decision-making things, and there's lots still to do. All right, so the second part of my talk I'm going to now turn to is that I'm going to run through a bit of sort of 5 years of work on dynamical systems meets algorithms. We've learned a great deal about how to design algorithms based on thinking about flows and dynamical systems. And these ideas hook up to all kinds of ideas in control theory and statistics, and really give us a new toolbox and a new way to think about designing algorithms. We're going to spend a lot of our time in continuous time, not discrete time. So we're not classical algorithm designers in that sense. And we're going to get brand new insights in continuous time that you cannot get in discrete time, at least easily. So I want to kind of give you an idea of this toolbox, because if you ask, well, what are you guys going to bring to mechanism design? What are you going to bring to microeconomics that's not already there? And we can say, well, learning algorithms, but what does that actually mean? Learning algorithms are often some kind of flow or gradient descent or something like that. And so you want to say, what mathematics is that bringing to the problem? And I'm going to argue that a lot, because there's been a lot of developments in non-convex optimization and high dimensional optimization and so on. All right, so again, this is sort of a summary of some highlights from 5 years from my group and others. Hopefully many of you have seen this, many of you probably have worked on this too. And so details of flow passed a little quickly here, but then I want to return by the end of the talk to some game theory problems where we're applying this kind of style of thinking. All right, so again, I'm going to just go quickly. So just first of all, acknowledge some co-authors here. Chijen, Praneeth, Rong, and Sham have worked on this particular paper. So this is kind of a starting point for a lot of our work. We're going to be talking about saddle points. And in the dynamical systems work that we kind of started with, saddle points are bad. You want to avoid them because they slow you down and getting down to the bottom of the hill. Of course, when we go to the game theory side, they're going to be good. We want to be attracted towards them. So that interplay is going to be interesting. And so this first line of work allowed us to start to think about non-convex optimization problems and how to bring dynamical systems idea to bear on that. So just again, flashing some slides here. I hope you all agree that non-convex optimization is important. And it's actually the saddle points which turn out to be maybe even the most problematic part of the problem. And it's one where we wanted to start to do more theory. Here's a saddle point, a positive eigenvalue and a negative eigenvalue. But really now we want to think about this embedded in millions of dimensions and oriented in some arbitrary way. And so if we start to arrive near this saddle point, we may get stuck there for a long time until we figure the escape direction. So how long? Is it exponential in dimension? Is it polynomial in dimension? And so on. So that wasn't known until a few years ago. Now it's really quite known. All right, just to remind you that gradient descent in the convex case is super well analyzed. You know that it converges to a global minimum, but we also know that the number of iterations of gradient descent in this setting is independent of the dimension, which is very striking. That's you can run gradient descent in infinite dimensions and in just as many iterations as in finite. Already gives you a little feeling of the power of gradient descent. But if you run gradient descent on this surface, especially in high dimensions, you're going to have all kinds of troubles. So the question is, how fast do you move past some of these saddle points and move towards a hopefully appealing nearby local minimum? All right, so this is what we worked on. Just to remind you, the kind of theory we're going to try to do here, this is Nestorov's theory for the convex case. And so in the convex case, you can define a first order stationary point. You can put a little epsilon ball around it. It's where the gradient nearly vanishes. And the rate of arriving at that via gradient descent is 1 over epsilon squared. Okay, so a Lipschitz constant and initial distance in the numerator and an epsilon squared. Notice there's no dimension dependence here. That is part of the theorem. Okay, so just let you look at that for a sec. a very minimal Buell-Stark theorem, non-asymptotic, no hidden constants, just this has really nailed the problem. All right, can we nail the problem similarly for the case of second order stationary points? Now we have saddle points. All right, well, we don't want to hit the second order stationary point. We don't want to hit the saddle points. All right, second order stationarity means the gradient nearly vanishes, but also you have a kind of a bowl shape that the smallest eigenvalue is greater than or equal to some lower bound. Okay, here, just below zero, if you will. All right. So in that setting, we analyzed a particular algorithm. We called it here in this particular paper perturbed gradient ascent. We knew already theoretically from some Morse theory we had done that just pure gradient ascent will take exponential iterations to arrive to get past the saddle points. Okay, exponential in dimension. But it turns out surprisingly, by adding stochasticity, you can get down from exponential to polynomial, but not only to polynomial. We were able to get all the way down to epsilon squared as a rate, and the dimension dependence was not exponential, it was polylogarithmic. Okay, so not exponential, not polynomial, logarithmic. Okay, so turned out to be log to the fourth power. That 4 probably could be made to vanish if you do some serious differential geometry. I'll just briefly allude to what we did. But anyway, I want to show the parallel to Nesterov here. Nestorov's gradient descent for convex problems was 1 over epsilon squared. Our perturbed gradient descent is 1 over epsilon squared for non-convex problems. And so really very, very close relationships here. Just to say a little bit about our proof technique, it is really differential geometry in high dimensions. We have near a saddle point, there's kind of a region where you're attracted into the saddle point, that green region there. Because the Hessian is smooth, but varying, that region is more of a kind of a, not a flat shape. It has a bit of a tilt to it, or a undulation. And if you hit that green region, you get sucked in. You want to know how thick that green region is. And so we did that with probability theory, doing a coupling argument. So we started a couple of Brownian motions a certain distance apart, and if they're close and they're both in the green region, they'll couple. If they're a little bit further apart, they will not couple. So you find a transition, a phase transition in the coupling time as a way to estimate the width of that green region. That gives you that logarithmic to the fourth power of D. Okay, that was one little vignette, if you will, about non-convex optimization in high dimensions with simple gradient-based methods with a bit of stochasticity. Okay, all right. So now you can start to ask about: are we done? Do we have a result that looks as good as Nestorov's? Are we are we done? So we can start to get lower bounds. Can we talk about acceleration and so on? All right. So here we now brought in another idea, which is turning out to be really important for not just this class of algorithms, but many other algorithms. And it's to bring in variational perspectives. So again, acknowledge some colleagues here, Andre Wibassono and Aisha Wilson in particular, students with me working on this. Andre is now at Yale and Aisha's at MIT. And I want to show you a little bit about the variational approach to dynamical system design for flows, for learning algorithms or, game theoretic algorithms. And I want to, kind of make a grand statement here about differentiation and integration. The fundamental theorem of calculus links them. Fields that are quite mature use a lot of differentiation, a lot of integration. They go back and forth all the time. So certainly physics does that, but also statistics has lots of both integrals and derivatives in it. The numerical disciplines like finite elements do as well. I would argue that optimization in that sense is not yet that mature. It's basically all derivatives. You rarely see an integral in an optimization book or an optimization paper. And so we're going to argue that that's a mistake, that we need to be doing integrals as well in optimization. All right, so again, sort of quickly here, let's return to now convex optimization with gradient methods, kind of Nesterov style. Let's add the fact that this algorithm will converge at a certain rate. That rate is 1 over k, where k is the number of time steps. This is just kind of a rewrite of the previous result, kind of flipped around. And you also will probably know that this algorithm is not the best you can do. If you're only looking at gradients, you can ask, is there some better way to use gradients to go faster? And it turned out there was. You can achieve a rate of 1 over k squared, which is meeting the oracle lower bound, with a algorithm that has got 2 parts to it. a y part and an x part. So it's a second order dynamical system, discrete dynamical system. This is Nesterov's algorithm, and hopefully you've seen it before. It has a little bit of a gradient descent and then a little bit of a rotation in it. All right, but the important part is that you can analyze this and show that you have this faster rate and that it's a second order dynamical system. All right, but it's a mystery where this algorithm really comes from, except from the genius mind of Yuri Nesterov. And still to this day, it's a mystery kind of how to think about this sort of more systematically. And we're going to argue, and others have argued, that we need to go into continuous time to understand this phenomenon, actually. All right, so just to kind of summarize, the 40 years of development in this kind of, Russian-inspired research of gradient-based methods. There's the gradient methods and there's the accelerator methods, and the acceleration phenomenon has been discovered and exploited in many, many kind of algorithms, not just convex, smooth settings. Okay, so here's just kind of a list of some of the things. The accelerator methods are mysterious. They're not descent methods, but they go down faster. So it's kind of interesting that you can get faster down the hill if you don't go straight down the hill, if you kind of go back up a little bit. All right, again, that feels a little bit physics-like, but we'd like to have a principle and sort of physics-like principles. All right, so on one slide, I've summarized what the line of research we did. We found a variational or Lagrangian perspective on acceleration in some generality. So we wrote down a Lagrangian, as you see at the top of the page there. It's in continuous time. It depends on x dot, and time, t, so it's a time-varying Lagrangian. And it's got some kind of degrees of freedom there, the alphas, gammas, and betas and gammas. Those are just diffeomorphisms to give you a space of algorithms in continuous time. They aren't the important part. The important part is the d sub h, which is the Bregman divergence. And it's between x and kind of a time-scaled x dot. And then subtracting off the function you're trying to go downhill on. So think of that like a kinetic minus a potential energy. So it's really kind of a time-varying Lagrangian. It's a variational framework, so you put this in a variational equation. The Euler-Lagrange equation is sitting down there halfway down the page. And once you do that, it's just two lines, and you get a differential equation popping out at the bottom of the page. So this is a master differential equation that has sort of most known acceleration algorithms in it in continuous time. Okay, so it's second order x double dot. It's got a damping term, and it's got some geometry in the third term. So it looks kind of complicated, but all these pieces really go together, and they're all important. And it reduces to known algorithms in many particular choices of alpha, beta, and h. Okay. With this, we're able to prove a convergence rate once and for all, a non-asymptotic rate, just by writing down a Lyapunov function. Aisha Wilson did this for her thesis. And we're able to discover a lot of structure about this particular set of equations. Because of this Lagrangian perspective, we can actually prove some kind of invariance properties of this underlying geometry that leads to invariance properties of the flow. All right, and in fact, this allowed us then to finally start to understand acceleration, I think, a little more deeply. All right, because what we were able to show with this formulation is that in continuous time, you can go as fast as you want. The Lagrangian tells you what path to follow, right? When you just solve the variational equation, right? But then I could do a change of time. I could simply use a different clock, and I could go along that same path faster. I could go 1 over t, like gradient descent. I could do 1 over t squared in the accelerated case, but I could also go exponentially fast just by changing the definition of the clock, right? And so, it's kind of like Einstein said, the clocks don't matter. So here, it shouldn't really matter. That's not the important part of the problem. And so, in fact, what we've discovered is that the rate itself in continuous time isn't the important part. It's the geometry that tells you what path to go down, right? But now there's a mystery, which is that in discrete time, we have lower bounds. These are these oracle bounds. You can't go arbitrarily fast. So if I took an exponential rate in continuous time, and I tried to discretize it to get an algorithm, something must break. And that's what we were able to show, that you are not able to discretize the rates that are exponential. There's going to be a phase transition in your ability to discretize differential equations. Okay, all right. And so the way we've been able to show this and actually prove that now is to think about symplectic integration. So if you don't know about this, it's a beautiful area of mathematics going back to Hamilton, Jacobi, and others, Poincaré. They were interested already in the end of the 1800s in discretizing differential equations. They had the equations of nature, Maxwell and Newton and all that, which were differential equations. And they wanted to discretize them in ways which conserved various conserved quantities like energies and momentums and so on. And they wanted to do that exactly. They wanted to do the real physics, but in discrete time. All right. And so the way to think about these ideas is that it's a flow, it's a vector field, if you will, but instead of a classical vector field where you have a single vector leaving a point and you follow that for a little while as you integrate the vector field, it's a different kind of field. It's more like a form field. You have a triple of vectors at a point, and that forms a little volume element. And as you slide along the flow, you want that volume element, it's allowed to shear, but you want to stay constant in volume. All right, so now you have a stability around the flow, and that volume element is often momentum or some other quantity that physics tells you needs to be conserved. All right, so it all fits together. It's kind of a numerical and physics story all together. And now, because it's all so stable, because of the way this flows is set up, you can now take much bigger step sizes, and that's the link to acceleration. All right. So just to show you a picture here, here's integration of the Bregman. Now we're working in Hamiltonian, not in Lagrangian space, but really the same idea. So it just kind of works. We plug in a problem description, we get out our differential equation, we integrate with a symplectic integrator, and it just works. And if you compare to Nesterov, this is on a different problem. These are all high dimensional quadratics. It's just as fast as Nesterov, but in fact, it's better than Nesterov in the following sense. I can now turn up the step size, and symplectic will move over to the left, just go faster, and Nesterov goes unstable. All right, so this gives you a sort of a richer numerical tool for thinking about optimization than classical acceleration, but it really also then gives you much more insight. All right, I'm going to skip this next little part just to say that we then, in line of research, put these ideas together. We took accelerated methods and we took the non-convex case with saddle points and we put them together, and we used our Hamiltonian Lagrangian perspectives to design all of the analysis and to design the algorithms. And it became fairly systematic. And so I'm just going to skip this. I think I just want to write down, here's kind of the analysis that used the Hamiltonian to design the analysis. So it's not just the algorithm design, it's actually the design of the theory here, which is coming out. And here's on one slide the actual result. The only thing to point out there is at the very top, there's a rate. And so it's not 1 over epsilon squared, it's 1 over epsilon to the 7/4. This was the first proof that acceleration helps you to move past saddle points quickly. Okay, so acceleration helps you in the non-convex setting as well as the convex setting. Another little bit here now I want to introduce into this story, which is that was all for differential equations. What if we go to stochastic differential equations? What if we ask about acceleration of diffusions? Because kind of the same ideas carry over to the stochastic case. And basically the literature had sort of had some debate about this. And the debate got resolved by realizing that much of the work had focused on overdamped diffusions, more like gradient-based, Longivan diffusion. So here's a Longivan diffusion at the top of the page. It's the gradient plus Brownian motion. So it's basically gradient descent in SDE land. And if you analyze the rate of that, it has a certain rate, and you would like to ask, can I improve that rate? All right, and that's where the controversy has arisen. And here are some rates. They go as d over epsilon squared for Longivan diffusion, kind of gradient-based diffusions. These are all recent results, by the way. And the question was kind of, can you do better than that? And the answer is yes, if you now go to a second order equation. And so we call this underdamped Longivan diffusion. It's got a gradient, but the gradient is now in the velocity term. So you have a velocity term with a gradient there, and you've got Brownian motion, and then you integrate the velocity to get the position. And now we're able to prove that the rate is faster. And let me just show you that here. Here's our rate. It's not 1 over epsilon squared, it's 1 over epsilon, so that's already impressive. But even more interesting, it's not d in the numerator. The dimension dependence is now square root of d. All right, so instead of getting stuck in all the ambient dimensions like a Brownian motion would sort of naturally do because it's random walk, you're somehow able to not get stuck in all the ambient dimensions. Okay, last little part of this story, then I'll kind of finish up with a couple of the applications to game theory. And here I definitely am not going to get into this is a whole talk of its own, but this is a paper where we finally were able to prove that symplectic integrators are rate preserving for these problems. So now here's where the last kind of interesting bit of physics came into play, which is a lot of the tools we were using in the earlier work were kind of classical conservation law based physics, like Hamiltonians. All right, so symplectic integrators, are in kind of one-to-one correspondence with Hamiltonian systems, meaning they're really good for these conservative systems. But optimization is kind of not a conservative system. It's dissipative. You want to not kind of go around a limit cycle. You want to go to a minimum. And so we need to apply symplectic ideas to dissipative systems. And this is not that common in the physics literature. All right, so this paper with Guy Franke, we have done that. And I just want to kind of allude that this is on the archive. If you're interested in kind of differential geometry of dynamical systems, you may want to look at this. We are looking now at Hamiltonian systems, and they are dissipative. And here's just on one picture, the basic concept, which is the blue manifold there is going to be the dissipative manifold on which we're trying to run our dynamics and which we're trying to discretize. We embed that in a bigger manifold, which has this these symplectic properties, and it's like you have conservation laws. And we run our integrator on that, and then we do a reduction. We do a gauge fixing, if you will, that takes us from the bigger manifold down to the smaller one. And so the algorithms now are transferred down to the smaller one. And that's the mathematics that allows you to say that you're going to have a rate preserving discretization. And not only rate preserving, you're going to have numerical stability as well. All right, so here's kind of a theorem. The decaying Hamiltonian is preserved. We're able to actually do backward error analysis and understand this. So I think we've now really have at least a particular way to understand why symplectic integration works and why this phase transition is happening. And now we can design algorithms in continuous time, both for deterministic and stochastic case. All right, so let me skip over some more details here. That's applying it to the Bregman-Lagrangian. Okay, so last 5 minutes of my talk. Let's now return to game theoretic problems and start to use our toolbox that we have for some of these problems and start to see some of the connections that are emerging. And these are by no means finished. This is all getting started. So here's a piece of work with Eric Mazumdar, is a student with me at Berkeley, in which we're interested in finding Nash equilibria. So Nash equilibria are saddle points in a particular kind of space, going uphill for one agent and downhill for the other agent. But they're particular kinds of saddle points. They're axis parallel. If you tilt a axis parallel saddle point, a Nash equilibrium, if you tilt it diagonally, it's no longer a Nash equilibrium, but it still is a saddle point, and gradient-based algorithms are not going to know the difference. All right, and that is a problem that it's, some people know about, but it's not that commonly known about it. So people will run gradient descent ascent algorithms trying to get them to at least converge. And then they put these in these high dimensional problems, like these variational autoencoders or GANs or whatever. And sometimes they get bad results. And sometimes the reason is because the gradient algorithms are converging to not at Nash equilibria. There are these tilted saddles. All right, so with Eric, we worked on this. And again, I don't want to get into details here, but this was the first setting. We looked just at zero-sum games. This applies beyond zero-sum games, but I just want to show you the results for zero-sum games. As you may know, simultaneous gradient descent, we're going down in one step and up in the other step, has issues in this domain. It doesn't converge necessarily. It might converge to limit cycles. It may not even converge. And then, as I alluded to, it could converge to non-Nash fixed points, which are tilted saddles. All right, so there's been a number of papers that have aimed at solving this by adding other terms to the gradient descent. And they do avoid the limit cycles, but they don't avoid the problem of arriving at non-Nash equilibria. So here on the left, you see a little picture where there are 3 Nash equilibria. Those are the green crosses. And there's a blue star in the middle, which is a saddle point, which is tilted. So it's a saddle point, but it's not a Nash equilibrium. And these algorithms, even these fixed up versions, start and they go to the nearby saddle point. And so for the green crosses, that's good. But for the blue star, that's not good because you're converging to something that's not a Nash equilibrium. So game theoretically, you would want to go there. How do you fix that? It's not so easy or obvious how to do that under gradient dynamics. All right, but we realized that the symplectic component that we referred to in the previous part of the talk, that was what gave you optimal acceleration. Here, it's exactly the wrong thing. The symplectic component is what is causing you to converge to arbitrary saddle points and not to Nash equilibria. So if you actually remove the symplectic component from the gradient field, we call that local symplectic surgery. And it's just a little algorithm written down there on 2 lines. Then this thing will go to Nash equilibria and only Nash equilibria. So you can see on the picture on the right, the red dashed line is starting to converge to the star in the middle, but when it gets to the neighborhood, it realizes, it sniffs it out and realizes that it's not a Nash equilibrium, and it moves away and finds a nearby Nash equilibrium. Okay, other little thing, and then I think this will be the end. I'll finish on this note. So again, with Eric and then Aldo Pacchiano, Yan Ma, and Peter Bartlett, colleagues at Berkeley, we're now taking this SDE Longivan, higher Longivan perspective, and we're applying it back to problems like Bandit algorithms. Okay, so in the Bandit algorithm, it's not just gradient descent for neural nets or something. It really matters that you get a fast algorithm, because bandits have to learn quickly if you're going to get a good regret, if you want to get a logarithmic regret. All right, so in bandits, there are really 2 main threads, as there are in most statistical problems. There's a Bayesian thread and there's a frequentist thread. And the frequentist thread puts confidence intervals on rewards, and it picks the upper confidence bound or something else like that, and then it analyzes that in terms of regret. And that's what we talked about earlier. That dates back to Lai and Robbins in the 80s. There's even an older tradition, which is the Bayesian one for multi-arm bandits, and that's called Thompson sampling, and it's pretty straightforward. You just have a Bayesian prior on each of the reward distributions for each arm. Once you sample an arm, you have some data. You can update that into a posterior, and you now just keep forming a bunch of posteriors for each arm, and then you sample from those posteriors to decide which arm to pick. Okay. All right, so can you analyze the Bayesian approach? Well, there's been much less work on that, and there's a number of problems here. But the main problem is that if you're outside of a very specialized sort of Gaussian setting or conjugate setting, then there's not a clear algorithm that you can run for the Bayesian approach other than MCMC, which only has asymptotic guarantees. So you're not going to converge quickly enough to be able to guarantee that you're making enough progress that you can get a logarithmic regret. All right, so that's been a real block in the literature for a long time. And so we went after that problem, and we used the kind of tools I've been talking about in the earlier parts of the talk. And long story short, we're able to show that these Longivan second order algorithms are fast enough so that they converge in the context of a bandit algorithm quickly, so that you can actually prove logarithmic regret for the Thompson sampling. Okay, so we've been able to resolve that open problem. And I just want to flash a couple of the slides that shows these results, and then I'm going to finish in a minute here and leave time for some questions. And so this is what I've alluded to, that posteriors from arbitrary posteriors lead to computational problems. So we were able to get around that. We have new posterior contraction rates for this problem. And so these are contraction rates or concentration inequalities for posterior distributions. So these are Bayesian concentrations. And then if you plug that into stochastic gradient Longivan as an analysis tool, that's how we're able to kind of put all this together. And so I don't want to get into details here, but not sure what happened to that slide. Something went bad there. Okay, I can't even show you something went wrong in my formatting here. Inside of that pink box, there is actually a concentration inequality for this. So anyway, we have the paper on the web. You can see it. Briefly, maybe this is just one last point to make. These are some empirical results. And it sort of gives a feel why Thompson sampling, even though it's the older method, is still probably the dominant one. Like in industry, you'll see many more people using Thompson sampling rather than UCB for like A/B tests. And the reason is, number one, people have a lot of prior knowledge about choices and historical data, but also the Thompson sampling is really quite good. So on the left here, we see regret as a function of iteration if you know the right prior. Okay, if your prior is a good one, it reflects the ordering of the arms. And so the blue curve at the top is UCB, so it has high regret, and the other curves are Thompson sampling, particular versions of Thompson sampling. So it's much better. What if you don't use the right prior, but you used improper prior? Every arm has the same prior, right? That's the middle curve, and you still see that Thompson sampling beats UCB significantly. On the right, you see if you use the wrong prior, just a prior that says, it reorders the arms incorrectly. Here, UCB, the blue curve is beating Thompson sampling by a little bit, but not very much. So, highly robust. All right. Okay, so I'm done. This slide I already had earlier in the talk. And so I just remind you of the top level kind of points I was making in the talk, that machine learning, this kind of emerging area of engineering, or kind of engineering field, if you will, has really focused mainly on just gathering data and finding patterns in data, and kind of thinking that's all you have to do. In fact, there's some well-known researchers that sort of say that's it. If you can do perfect prediction, that's kind of solves all problems. And I just hope you will agree, especially after this talk, that that's not right. That decision making is equally part of the problem, and it involves all kinds of strategies around data analysis. It depends on how you sample, it depends on what data you think about, it depends on how you use error bars, it depends on dialogues about decisions, and so on and so forth. All right, so I'm going to finish there, and I'm happy to take questions if there are any.
All right, thank you very much, Professor Jordan, for the wonderful and very informative talk. So there are a bunch of questions in the chat box. Maybe I can relate that to you first. People got very interested in the talk. So I guess Colin asked, what are the phases in the saddle point, the green region you are talking about? I guess he was talking about like the escaping saddles, that point, the green region.
Yeah, the green region is just kind of a notional region that around a saddle. So think of a saddle point in the middle of all that, all right? And there's a region in which the flow is mainly determined by the positive eigenvalue that you flow towards the saddle point, okay? Now, outside of the green region, you'll start to see a little more contribution from the negative eigenvalue, which makes you exponentially fly away from the saddle point, right? So if you can kick yourself out of the green region, that's good. You'll see the negative eigenvalue, you'll leave very quickly out of the saddle point. So getting stuck near the saddle point means you're too long in the green region, right? So if the green region is really, really thick, that's a problem, okay? That means we know we're gonna get stuck for a long time next to this saddle point until we finally find the way out. So we need to estimate or upper bound the width of that green region, okay? So it's kind of the region where the negative eigenvalue, or maybe it's only one or several of them, is really small, all right? And again, if you're doing, it's really a differential geometry problem, but maybe we're not good enough in differential geometry, we use probability theory instead to kind of skirt the need to do the differential geometry. So I'll bet you if you're really good in differential geometry, you can probably make that logarithm of the fourth power go away. It'll probably be not, it'll still be logarithm. It's not going to go to no dimension dependence, but probably the 4 will go away.
See. Wimbo also asks, can you explain more about the expression of the Bregman Lagrangian?
Okay. Actually, I see on my, some of my listeners here include Andre Wibisonen and Aisha Wilson, who are the people who developed this back at Berkeley. So they could probably do a better job than me. Okay, so I don't think I'll bring back the slide, but these Lagrangians are, really, or Hamiltonians are really differences or sums of terms, right? It's Hamilton's perspective. And the first term is an energy term. And so in fact, in the Bregman Lagrangian, the first one we looked at in that first paper, the Bregman divergence is the kinetic energy. And Bregman divergences have this auxiliary function that helps you to measure distance. So it's d sub h, and that h function, is used to kind of get the gradient of that to measure distances. If you set h to be quadratic, right, then the Bregman divergence reduces to Euclidean distance. It's just a variational way to write Euclidean distance. And when it reduces to Euclidean distance, that first term becomes literally 1/2 v dot squared. It becomes literally a kinetic energy. All right, and so we have a kinetic energy minus the function f of x, again scaled perhaps. And so that's literally a kinetic energy minus a potential energy, and that's what Lagrange invented back, in the 1800s. All right, and so we're just trying to write down an action or a way to evaluate a path. And as I alluded to, this line of research, that Aisha and Andre were responsible for, found a way to describe those paths and related to that the geometry of the problem. And so then the rate comes in as a secondary factor. And what we were later able to discover in this later work is that you can preserve that rate with symplectic integration. And we could prove that now.
I see. Thank you. So another question from Diego and Tao, I guess they are mostly related, asking that does the local symplectic surgery method apply to n-player games? in case it doesn't, why not? Because
yeah, no,
we
it
know
does.
this. Yeah,
It
its
does.
unplay games can be also tasked because its unplay games can be reformulated as solving the variational inequalities.
Yeah,
so
no, it does,
kind of
and that style of work does apply to variational inequalities, and so we're finally starting to do some work with at the variational inequality level. We have a paper just recently with Wenshuo Guo, where we're looking at variational inequalities and using this kind of technology to solve them for a class of Bayesian games. But that's completely new open territory. So if those of you know about that, I'd highly encourage you to, yes, use this kind of dynamics for variational inequalities. I think there's a lot to do there. Also, I might add, there's another paper I'm working on with a colleague where we're looking at applying these variational kind of ideas to constrained optimization. And the beauty there is that the constraints can come in at not just the positions, but at the velocities and the accelerations. You could put constraints in its forces and so on. And that goes right into the kind of physics-based perspective here. And you can get rates of constrained optimization without projections and without, kind of, classical constrained optimization techniques. So that's another emerging area. We should have a paper soon on that. Very excited about that.
I see. That sounds very exciting. So in the interest of time, maybe we allow one question from the audience. Or whoever have question, you can unmute yourself and ask a question. So if not, I have a quick question. So regarding the one you found the Nash equilibrium in zero-sum games using this local symplectic surgery method, do we know any kind of non-asymptotic guarantees for that? Like how long does it take to find that point?
Yeah, no, it's a great question. So the answer I was going to give you for a few days ago was that we know nothing really, and so okay. And I was going to kind of say that that's not unreasonable. If you remember that little plot that I showed you, the red path headed towards the bad equilibrium, the bad saddle point, right, and then it moved away. All right. So the time it took to get to an actual good Nash equilibrium was long because it kind of got diluted for a little while. Right. And so a good rate analysis would kind of take all that into account. And so to me, it felt like we just didn't know how to do that yet. So you could analyze the rate of the other algorithms, and they're going to be fast, but they're going to the wrong answers, right? And so we needed to kind of get that in there. But Eric, my colleague here, just told me the other day he's figured that out, and I don't know what he means. But we're now doing a revision of that original paper, and I don't know if Eric's on the line here, but there is some possibility of progress on that. But yeah, I mean, there is a little issue here, though. You got to kind of worry about rate to what? Is it a local rate? Does it take into account this kind of foray that you had to make, possibly in the neighborhood of some bad things? But I'm kind of guessing it's kind of like our saddle point story, is that the landscape has got some bad things littering it, and you just want to make sure you don't get stuck near them too long. And that's kind of what we were able to do for saddle points in the optimization case. Something like that is perhaps happening here as well.
Got it. So in the interest of time, we may have to stop here. And thank you, Professor Jordan, very much for joining us today. And thanks everyone for participation. I'm looking forward to seeing you in the next talk. Thank you.
All right. Thank you.
Thank you very much.